Okay, good morning. This is Professor David Reyes. Okay, I got a random topic for this morning. It's this morning here in Los Angeles. My random topic will be it's a calculus that involves three variables. So calculus that includes three variables. Calculus containing multi-variables. I think this will be under the topic partial differentiation. So this is actually an additional topic under differential calculus. And that topic under differential calculus was actually partial differentiation. Differentiation, okay, synonymous to differential. So our topic for tonight will be a topic on differential calculus, and this falls under partial differentiation because under partial differentiation, a given function could be as a function of three variables, something like that. Okay, I will try to give you the concept on how we use partial differentiation, a multi-variable thing. Multi-variable. It could be two variables or three variables, but for tonight, I will be giving you three variables. If we are given y as a function of three variables, x, z, and w, that's why it is multi. Okay? It is multi. So meaning y is given as a function of x, z, and w. To take the total differential of this one, the total differential of y will be dy. Okay? And this should be equal to the partial derivative of y with respect to x times dx plus the partial derivative of y, still y, with respect to z times dz plus the partial derivative of y with respect to w, the last one, the last variable, with respect to w times dw. Okay, there is a new, what you call this symbol over here. Under differential calculus, this symbol here, it's just like a number 2. We read this partial. Partial derivative. Okay? Okay, I will repeat it. Total differential y will be the partial derivative of y with respect to x times dx, partial derivative of y with respect to z times dz, partial derivative of y with respect to w times dw. We just follow this. The first one will be with respect to x, the second one will be with respect to z, and the third one will be with respect to w. That's why this is a calculus that involves multi-variable. Okay. Where dy is the total differential of y. Total differential is meaning increment. If we are solving increment, right? And this, if we try to read this one, it should be read the partial derivative of y with respect to x. Partial derivative of y with respect to x. Okay? And treating, okay, z and w as constant. If you are differentiating with respect to x, treat z and w as constant for the first one. For the next one, the partial derivative of y with respect to z, we are now differentiating with respect to z, the one in the middle. It should be read the partial derivative of y with respect to z, treating the other two variables as constant. We are differentiating with respect to z, right? So treat x and w as constant for this partial derivative. Okay? The last one, the partial derivative of y with respect to w. we are to differentiate with respect to the third variable, with respect to w. So this should be read partial derivative of y with respect to w. Since we are differentiating with respect to w, treat at this time x and z as constant. So treat x and z as constant. Okay? That's it. That's the concept upon how to read this one. Partial derivative of y with respect to x, okay? Z in w will be constant. Partial derivative of y with respect to z, x in w will be constant. And for the last one, the partial derivative of y with respect to w, x and z will be constant. Okay? So, where do we need this formula? We are to use this formula in practical application problems. That will be the problem I will be giving for tonight or for this moment. Okay, I will try to read the problem. A box is 36 by 48 by 60 centimeters. We are given the rectangular box. The length, width, and height are given. So this is 36 by 48 by 60 centimeters. If it is to be painted 1/10 centimeter thick, the thickness of the paint that will be painted, the thickness is 1/10 centimeter. Find the CC. CC meaning since the unit of the length is centimeter, if we try to take the volume, it will be CC meaning cubic centimeter. So CC here is cubic centimeter. Find the cubic centimeter, so meaning cubic centimeter, it's the volume. Find the CC of paint used up. Okay, that will be an application problem of this partial differentiation here. That involves three variables. So this is a calculus that involves three variables. And that calculus is actually differential calculus. Okay, we are given a box 36 by 48 by 60. The length, of course, the longest one will be the length, right? So I place it here, the length will be 60 centimeters, and the width will be 48 centimeters, and the height will be 36 centimeters. Length, width, times height. Okay, I place it here. The product of WL will be the top and bottom. The product of this times this will be the bottom portion plus the top portion. And the product WH, this one here, the one facing us. Okay? The product W times H is actually the two sides. It should be this side here plus the other side. And the product HL, where is HL? This one. This is also L, right? The product H times L, this side here and this side. The product HL contains also two sides. Why I am giving you this one? Because in the computation of the volume, we are to exaggerate that we are painting 8 sides of the box. So this is 2, is it 2? 6, right? Up and down, yeah, it's 6. Okay, let's bring out the solution of this one by using the concept of partial differentiation. The volume for any rectangular object will be the product of length times width times height, right? The volume of this one will be the product of length times width. That's the bottom area. So to take the total volume, we must have to multiply that by h. So actually, it's the length times width times height. That's volume. Okay? So how do we compute for the volume that is being used to paint this box? It is just a differential volume. Okay? Because if we don't use calculus over here, we will be subtracting volumes of two rectangular boxes. But there is a shortcut for that one, and that shortcut is actually partial differentiation. Okay? So if we are given volume as the product of length times width times height, So this is actually almost similar to the equation y as a function of xjw, where this length here is variable, width is variable, h is variable, and volume is variable. So if we try to take the total differential of this is three variables, right? So the total differential b will be equal to, we have to differentiate this volume here with respect to L first. So partial derivative of volume with respect to L times dl. The next one will be the partial derivative of the volume with respect to the second variable W times dW. And the third one will be the partial derivative of the volume with respect to height, the third variable, times differential height. So this is actually the formula on how to get the volume of the pen that is needed. Okay? Later on, I will try to give you the other solution without using calculus. Okay, because if we paint all the sides, actually the box will become thicker, right? So to get the total volume of the paint that is needed, you subtract two volumes. But in here, this will be the shortcut. Where dB here is the paint needed in cc. Okay? Okay, let's try to take the partial derivative of volume with respect to L. Okay, we are differentiating with respect to L. So the only variable on the right hand side for the meantime will be L. So treat W and H as constant. So this should be WH. The derivative of L with respect to itself is 1. So the partial derivative of volume with respect to the length will be the product WH. Next one. We have to differentiate the volume with respect to the second variable. The partial derivative of volume with respect to the width, the second variable, should be equal to, we are differentiating with respect to W, right? So L and H will be constant for the meantime. So this will be LH, and the derivative of W with respect to W. On this second partial derivative, we are to differentiate with respect to W. So W is variable, and the derivative of W with respect to itself is 1. So the partial derivative of volume with respect to W will just be simply LH. The third one, the third variable is H, right? So the partial derivative of volume with respect to the third variable H, okay, should be equal to, we are to differentiate with respect to H. So L and W for the meantime will be constant. So LW times the derivative of H with respect to H is times 1. So the partial derivative of volume with respect to H will be the product LW. Okay? So we now know these three values here. Okay? That's why the topic for tonight is a calculus that involves multi-variables, right? So DL now, if we try to write now the formula, DL now will be equal to, okay, let's compare first for the thickness, the change in the thickness. Because if we try to paint all the sides, the length should increase by a small amount, and that small amount is the thickness of the paint that is needed, right? So for all the thicknesses, DL, DW, and DH, the value is actually 2 times 1/10. Why times 2? Like the bottom portion. We paint the bottom portion, so we add a certain thickness, right? And we paint the top portion, so we add also a certain thickness. So for the top and bottom, it will be times 2. The two other sides, it will be times 2 also. So I place it here, DL equal to DW equal to DH, and this should be equal to 2 times 1/10. And this is 0.2 centimeter. Right? The total thickness added to the length, width, and height will be twice the thickness of the paint, right? So this is 2 times 1/10. So going back to this equation here, it will be differential volume now will be WH. WH is 48 times 36 times 0.2. The next one will be LH. LH will be 60 times 36 times 0.2. The third one will be LW. LW will be the product of 60 times 48. So this is 60 times 48 times 0.2. Okay? Oh, have you got my explanation? If we paint the box, the length should increase twice, right? The top and bottom. And the two other sides, it will be times 2 also. And plus the two other sides, it will be times 2 also. So this is 0.2, the common factor will factor out 0.2. This is now algebra. 36 times 48 will be 1728, 60 times 36 will be 2160, and 48 times 60 will be 2880. A common factor is 0.28, right? So this is 0.2. You will not use pentas here, it's just a simple addition. So the summation of this one will be 68, this is 0.2. Therefore, differential volume now will be 1383.6 cc, or meaning cubic centimeter. So the total paint needed is 1383.6 cubic centimeter. That's the solution using partial differentiation that involves 3 variables. So this is a calculus that involves 3 variables, meaning multi-variables. Okay? The box is just something like this. If we try to paint all the sides, if this is the length, the length should increase twice, right? One here and one here. Okay, this space here, there will be a pin here, and there is a pin here, so it is also times 2. That's why there is times 2 over here. And this side here, or this side, or this one, there's a thickness here plus a thickness here, so it's also times 2. So the value of DL, DW, and DH is 2 times 110, and that is 0.2 centimeter. And if we try to compute the volume needed, if we do not use differential calculus, okay, you'll be subtracting a volume of 2 rectangles, okay. The other one is bigger because there is a thickness 0.2, right? Plus the original volume 38 times 48 times 60. If you try to subtract that one, what will come out should be 1383.6 cc. Okay, good morning from Los Angeles. This is Professor David J. De Los Reyes.